I spent 30 years staring at equations about time, and I can tell you this. You're thinking about it wrong. Not slightly wrong, fundamentally wrong. And I was wrong too, for longer than I'd like to admit. You think time is a river that carries everything forward at the same rate. You think it's something that happens to you the same way it happens to everyone else. You think your watch and my watch and a watch on Jupiter are all ticking away in perfect synchrony, measuring something absolute and universal. No, they aren't. Time is personal, it's local, it's flexible. And the thing that determines how fast your clock ticks compared to mine isn't where you are. It's how fast you're moving. Not metaphorically, actually moving through space. Let me show you why. In 1967, when I was still walking, I sat in a lecture hall at Cambridge and heard something that didn't make sense. A visiting physicist was explaining Einstein's special relativity, and he said something that seemed like obvious nonsense. Moving clocks run slow, not broken clocks. Moving clocks. As if motion through space could somehow affect the machinery of time itself. I remember thinking he must be speaking metaphorically, or there must be a catch, some tiny experimental error that would eventually reveal the whole thing as an approximation, because if what he was saying was literally true, then time wasn't what I thought it was. Time wasn't the stage on which physics happened. Time was part of the physics. It took me years to accept it. Not because the math didn't work. The math worked beautifully. Because it meant everything I intuited about reality was wrong. Here's the experiment that changed everything, performed in 1971 by physicists with atomic clocks and commercial aircraft. They took 4 cesium atomic clocks, the most precise timepieces ever built, accurate to billionths of a second. They synchronized them perfectly. Then they put 2 on aircraft and flew them around the world, one eastward, one westward, while the other 2 stayed on the ground. When the aircraft landed and they compared the clocks, they weren't synchronized anymore. The clocks that flew eastward, with Earth's rotation, moving faster relative to the center of the planet, had lost 59 billionths of a second. The clocks that flew westward, against the rotation, moving slower, had gained 273 billionths of a second. Not because of turbulence, not because of temperature changes, or air pressure, or electromagnetic interference, because time itself had passed at different rates. The moving clocks experienced less time than the stationary ones, not measured less time, experienced less time. The universe aged around them while they stayed younger, by billionths of a second, but measurably, undeniably younger. That's when I realized time isn't an external thing that happens uniformly to everything. Time is something you experience based on your motion through space. Your past and your future aren't the same as mine unless we're moving together at the same speed. Let me take you inside this to show you what's actually happening. Imagine you're on a train moving at 90% of the speed of light. Not a metaphor, an actual train, one that somehow has enough energy to reach 270,000 kilometers per second. You're sitting in your seat with your watch. From your perspective, everything feels normal. The watch ticks at 1 second per second. You breathe normally. You think at normal speed. As far as you can tell, time is passing exactly as it always has. But to me, standing on the platform watching you pass, your watch is running slow. Not a little slow, dramatically slow. For every hour that passes on my watch, only about 26 minutes pass on yours. You're moving through time at less than half the rate I am. From my perspective, you're aging in slow motion. Your heart beats slowly. Your thoughts happen in stretched-out intervals. The chemical reactions in your cells proceed at a crawl. But here's the thing that makes this truly strange. From your perspective, It's my watch that's running slow. You look out the train window and see me standing there with my watch ticking at 26 minutes per hour, while yours ticks normally. Motion is relative. There's no absolute standard of rest, so each of us sees the other's time dilated. This isn't a paradox. It's how the universe works. Time is relative to motion. Your timeline and mine only synchronize if we're moving together. The moment we're in relative motion, we slice through space-time at different angles, and our clocks diverge. The mathematics of this is elegant and brutal. The time dilation factor, how much slower a moving clock runs compared to a stationary one, is given by the Lorentz factor, 1 divided by the square root of 1 minus your velocity squared divided by the speed of light squared. At everyday speeds, the factor is so close to 1 that you'd never notice. At 90% of light speed, it's 2.29. At 99%, it's 7.09. At 99.9%, it's 22.4. The closer you get to light speed, the more extreme the dilation becomes. At 99.99%, a year for you is almost 71 years for everyone else. You could travel for what feels like 10 years and return to find 700 years have passed on Earth. Which means this: if you want to travel to the future, you don't need a time machine. You just need to go very, very fast. In 1985, I realized something that made me laugh out loud, sitting alone in my office at 3 a.m. The cosmic speed limit, the thing that seems like it traps us, that seems like it forbids us from ever reaching the stars, is actually the mechanism that would let us cross the galaxy. Not by going faster than light, by going close to it and letting time dilation compress the journey from your perspective. Here's what I mean. Proxima Centauri, the nearest star system, is 4.37 light-years away. If you traveled in a conventional rocket at conventional speeds, say the speed of the Voyager probes, about 17 kilometers per second, it would take 75,000 years to get there. You'd be dead. Your children would be dead. Your civilization might be gone. But if you accelerated continuously at 1 gravity, the comfortable pull you feel standing on Earth right now, you'd reach 95% of light speed in about 3 years of your time. And from your perspective, the universe around you would contract. Distances would compress. The 4.37 light-years to Proxima Centauri would shrink to just over a light-year. You could reach it in about 3.6 years of subjective time. Keep accelerating past Proxima. At constant 1-gravity acceleration, you'd reach the center of the Milky Way, 26,000 light-years distant, in just 20 years of your time. The Andromeda Galaxy, 2.5 million light-years away, in 28 years. From Earth's perspective, millions of years would pass. Everyone you knew would be dead. History would have happened and been forgotten. But from your perspective, the only perspective that matters to you, you'd have crossed the galaxy in less than 3 decades. Time dilation isn't a bug in the laws of physics. It's the feature that makes the universe traversable. But here's where reality charges its price, and where my stubborn optimism met immovable mathematics. The energy required to accelerate to those speeds is staggering. To accelerate a single kilogram to 90% of light speed requires 1.8 times 10 to the power of 17 joules, roughly the energy output of a large nuclear power plant running for several days. For a spacecraft with crew and supplies, say 1,000 tons, you'd need more energy than humanity currently produces in a year, just to reach 90%. At 99% of light speed, the energy requirement doubles. At 99.9%, it's 11 times higher than at 90%. At 99.99%, the energy approaches infinity. There's a wall built into the mathematics. You can get arbitrarily close to light speed, but you can never quite reach it. Every additional decimal place of speed, every increment closer to that limit of 299,792,458 meters per second, costs exponentially more energy. The universe won't let you arrive at the limit itself unless you're massless, like light. For decades, I thought that was the end of the story. The speed limit was absolute. Time dilation was real and exploitable, but the energy costs made it practically impossible. We could dream about crossing the galaxy, but we couldn't afford the ticket. Then, in 1994, a physicist named Miguel Alcubierre published a paper that made me reconsider everything. He proposed something extraordinary. What if you didn't move through space at all? What if you warped space itself, contracting it in front of you and expanding it behind you, so you surfed on a bubble of distorted space-time? You wouldn't be moving faster than light through space, you'd be stationary in your little bubble, but space itself would be moving, carrying you along, like standing still on a moving walkway at an airport. The math worked. It didn't violate relativity because you weren't moving through space faster than light. Space was moving, and relativity has nothing to say about how fast space itself can expand or contract. The cosmic speed limit only applies to objects moving through space, not to space moving itself. I was genuinely excited. For about 2 weeks. Then physicists started actually working through what Alcubierre's warp drive would require, and the excitement turned to despair. To create the warped space-time bubble, you'd need negative energy, a theoretically possible but practically impossible substance that has never been found in nature. You'd need amounts of it equivalent to the mass of Jupiter. You'd need to shape and control it with precision we can't even imagine achieving. And even if you somehow built the thing, you'd have no way to steer it or turn it off once you were inside. The warp drive wasn't impossible in the way faster-than-light travel through space is impossible. It was impossible in the way building a ladder to the moon is impossible. The laws of physics don't forbid it, but the engineering is so far beyond us that it might as well be magic. I'm 82 now, sitting in my office at Cambridge in 2024, looking at the same equations I've been looking at for most of my life. My body stopped obeying me decades ago. I communicate through a machine. I breathe with assistance. My personal experience of time's cruelty is measured in years of immobility, not in relativistic calculations. And yet, the time dilation is still true. The mathematics still works. The universe still bends time for objects in motion, still compresses their experience of duration, still makes the galaxy crossable from the perspective of the traveler, even if millennia pass everywhere else. The cosmic speed limit isn't a cage, it's an invitation written in mathematics. It says, you can't break this rule, but you can use it. You can turn motion into time, space into duration, distance into youth. You can cross the stars by surrendering the world you left behind. I spent my life trying to understand time, what it is, how it flows, whether it had a beginning, whether it will have an end. I studied black holes where time stops, singularities where it breaks, the Big Bang where it began. I wrote equations describing the universe's first moments and its final whisper. But the simplest truth took the longest to accept. Time isn't absolute. It isn't universal. It isn't the same for you as it is for me unless we're moving together through space. Your now and my now are only synchronized by coincidence of velocity. When you look up at the night sky and see stars light years away, you're not looking at them as they are now. You're looking at them as they were when their light left, years or centuries or millennia ago. Their now and your now are separated by the time it took light to cross the distance between you. And if you were to accelerate to near light speed and travel to one of those stars, time itself would bend around your journey. You'd arrive having aged only years, while Earth aged decades or centuries. You'd step off your ship into a future you could reach, but never return from. That's what the speed limit teaches us. Not that we're trapped, that we're choosers. That the price of crossing the cosmos is time itself, the time of everyone you leave behind, measured in years that pass while you stay young. The universe doesn't have to make this easy. It doesn't have to let us travel at all, but it does, in its own strange way, on its own terms. It offers time dilation as a gift and a curse, a possibility and a price. I made my peace with physical limits long ago. The limit on my movement, the limit on my voice, the limit on time I have left. Learning to work within constraints, to find beauty and possibility in what remains, rather than mourning what's forbidden, might be the most important thing physics ever taught me. The cosmic speed limit is the same kind of boundary. Not a prison. Information. It tells us the fundamental architecture of reality, that space and time are woven together, that motion through one affects your rate of passage through the other, that the universe has structure and rules we can understand even if we can't break them. I don't know if humanity will ever build ships that can exploit time dilation to cross the galaxy. I don't know if we'll solve the energy problem, the engineering problem, the philosophical problem of surrendering Earth's timeline to travel to the stars. I won't live to see it either way. But I know this: time is not what you think it is. It's not a river carrying everyone forward together. It's personal, flexible, strange. It's part of the same fabric as space, woven together in a geometry that bends with mass and stretches with motion. Your watch and mine are only synchronized because we're both roughly stationary on the surface of the same planet. Move, and our times diverge. Accelerate to near light speed and you leave my timeline entirely. That's not science fiction. That's physics. Measured, confirmed, absolute. The universe is stranger and more generous than we imagined. The limit that seems to trap us is the mechanism that could free us. And time, stubborn, flexible, personal time, is the price and the possibility of everything we might become.